All right, AP Chemical Chemist. Let's start talking about Part C, the nucleus. Again, most of this is review from last year for most of you guys. So, these are some of the models of the atom. The first is what we call the Plum pudding model. Okay, once it was determined that atoms are made up of negative and positively charged particles, J.J. Thomson and his team proposed that the structure of an atom looked like a plum pudding. Okay, it had a bunch of positive charge in there, and it had little negative electrons, right? Right there in the middle of the sphere of that matter, with negative electrons embedded in it. Because he said that the positive, negative charges attract, and like charges repel, so they'd hang out together, right? So most models must be tested, and the search was on to find evidence to support this. So one of his students, Ernest Rutherford, used radioactivity to test this theory. Now, what is radioactivity? It's the spontaneous emission of radiation or energy by an atom. Rutherford studied emissions from the unstable element uranium. Large elements like uranium contains an atomic nucleus that can be either stable and does not change, or it's radioactive, meaning that it wants to transform or decay into another element after a certain amount of time. Now, decay can be very short, like a fraction of a second, or it can take millions of years for it to decay. So what happens is this is a very unstable element, so it would break, okay? And it would break away into smaller nuclei and smaller particles, right? And it releases energy. So there's three types of radiation were discovered by Ernest Rutherford. One is what we call an alpha ray, okay? And these are alpha particles, which were positively charged particles, and had a mass that was like 4 times that of the proton. So it had like 2 protons and 2 neutrons, and that's what we found out. Then there were beta rays, and these were beta particles. And we found out those were electrons. Then you had gamma rays, and this was a form of light energy, and it was very high energy. So he could put uranium in there, and it would shoot off these little particles. Okay, and he could shoot it through something, right? And if he shot it through a charged plate, a positive, an anode, and a cathode, then the negative, the beta particles, the electrons, would deflect toward the positive plate, the cathode, anode, rather. Okay, and the negative charged particles, alpha rays, okay, or the positively charged particles, would deflect toward the cathode. The gamma rays would just go right on into this photographic plate. So, which are particles? Well, let's see. The beta rays and the alpha rays were particles. Gamma rays, nah, that was just light energy. So it couldn't be A, it couldn't be B. So it was D. Alpha rays and beta rays. D. Now, beta particles are attracted to what? A positively charged plate, indicated that they are what? Negatively charged? Well, they are. They're attracted toward the positively charged plate because they're electrons and they're negatively charged, so that should be A, and it is. Alpha particles are positively charged because they got protons, so that's B. Now, gold foil experiment. This is famous. We talked about it. We played with it a little bit. So Geiger and Marsden, who was on the team of Ernest Rutherford, they shot a beam of alpha particles, those positively charged particles, at a thin sheet of gold foil, right? And then they observed the scatter pattern of these particles. Now notice, most of them went right through the plate. A couple of them are deflected that way, and some of them came right back at them, right? Some of them were deflected that way. So, if this was the plum pudding model, the positive and negative charges would go right through it. They'd be evenly distributed throughout the atom because the positive charge would hit the negative, would hit the positive, and then it'd knock back. So if this is correct, these alpha particles would be slightly deflected by these weak electrical fields as they pass through the foil. So he expected all the alpha particles to pass through the atoms in the gold foil and be deflected by not very much, a couple of degrees. This was very surprising to him, right? Very surprising to him. Some of them did deflect like they expected. Okay, most of them went right through the foil. That's what they expected. But then they noticed that some of them came almost straight back to them. This was totally unexpected. So what this indicated, okay, about the locations, and there's the direction of the alpha particle. One went right through. Okay, one hit this positively charged particle in the middle of the gold. It was deflected off right through, and this one was deflected right back. So these protons are clustered together in the center of the atom. So this was the only way to account for these angles that they were measuring, right? Was and what he hypothesized was that the positive charge was a very small part of the volume of that atom. Most of it was empty space. Most of it went straight through. Now, this small, very dense nucleus had to be lie in the center of a mostly empty atom. Now, we know that the radius of the nucleus is now 1/10,000th of that atom. This is very small. Very small. Oops. So this is what he said. I remember 2 or 3 days later that Geiger coming to me in great excitement and saying, we've been able to get some of the alpha particles coming backwards. It was quite the most incredible event that ever happened to me in my life. It was almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you. Again, by the math, that's the way it should have been. So, the gold foil experiment performed in Rutherford's lab did what? Led to the discovery of the atomic nucleus? Was the basis for Thomson's model of the atom? No, he had the Plum pudding model. Used the deflection of beta particles by gold foil? No, they were alpha particles, so it has to be B, and that's what it is. In the Rutherford nuclear atom model, the heavy subatomic particles reside in the nucleus. The principal subatomic particles all have essentially the same mass. The light subatomic particles reside in the nucleus. Mass is spread essentially uniformly across the atom. Let's see. A, the heavy, okay, the protons, subatomic particles reside in the nucleus. So, after the discovery of the electron, scientists believe that there must also be a positively charged particle in the atom. All right. And to look for these, instead of using a cathode ray tube, they used an anode ray tube, where the juice would come from the anode and go to the cathode. And then they would put a little device with holes in it in the cathode so those particles could move through it. They found that these particles were indeed moving from the anode to the cathode. Okay, so since they move toward the negative plate, they must be positive. So the anode rays were referred to as protons, which were found to be much more heavier than electrons, 1840 times the mass of an electron. And Millikan already discovered the mass, or calculated the mass. And since the heaviest anode rays in oxygen were found to be 8 times heavier than those in hydrogen, then you could assume that oxygen had 8 protons compared to hydrogen's 1. So the number of protons, we found this out, and write this down, remember this. The number of protons an atom has is different for each element on the periodic table. So the number of protons determine what the element is. Which of the following is true regarding protons? They were originally called cathode rays? Nah. They move faster than cathode rays? Nah. They have a larger mass than electrons. Well, 1840 times larger than the electron. Okay, so it has to be C. That's what it is. Which of the following is not true regarding protons and electrons? Both were found in all atoms. Well, they were found in all atoms. Their charges are equal in magnitude. Well, the positive charge is equal to the negative charge. Protons are significantly heavier than electrons. Yes, they are. All elements have the same number of protons and electrons. Notice how that read. All elements have the same number of protons and electrons. Well, that's got to be wrong. So that is because each element has a different number of protons and electrons. The mass of an electron was found to be 9.1 times 10 to the minus 31st kilograms. It's pretty small. So what is the mass of a proton? Well, if you take that, multiply by 1840, you'll come up with 1.67 times 10 to the minus 27th A. All right, guys, that's all the filming we're going to do tonight. I'm going to put these out there. We'll discuss these throughout the week. You guys have a wonderful evening, and we'll talk to you later. Coach Scott out.